Hello, chemistry students. Today we're going to talk about counting stuff. And what I mean by that is counting the number of things in stuff. How many particles, how many atoms, how many molecules you have in an amount of substance. So, knowing how much stuff you have is really important in chemistry because chemistry is all about ratios. Like here we have two H2O molecules. These are two water molecules. And we could see that they were made from an oxygen molecule with two O's stuck together and two hydrogen molecules. Knowing that these were in a 2-to-1 ratio was really important to have enough atoms to form the molecules that we needed. However, we can't really count individual atoms or molecules because they're too small and there are a lot of them. So we need some special units and some special methods in order to do this accurately. So just as a quick tangent, in English, we use special words to count things. So like if you ever refer to a couple, you're usually referring to two things, or a dozen, you're referring to 12. This isn't used very often these days, but a score is 14. A gross is 144, a dozen dozens. And there's a funny one called a googol, which is 10 to the 100 number of things. And these are all English words that mean a certain amount of things. And this is going to be important in chemistry, and I'll kind of get to that in a second. Um, but if we're trying to count something that there is a lot of, it's kind of hard to do so. Like imagine if I asked you this question: to rank in order of least to most between the grains of sand on Earth, the stars in the observable universe, the molecules in a drop of water, or the cells in your body. Pause this video for a moment and just think about these four things and see if you can come up with a ranking. So the actual values for these things, for grains of sand on Earth, there's about 8 times 10 to the 18. Stars in the observable universe is 1 times 10 to the 24. Molecules in a drop of water are 2 times 10 to the 21. And cells in your body are about 4 times 10 to the 12. So stars in the observable universe is by far the biggest, but there's a surprisingly close amount of molecules in a drop of water. And this is an important idea because it shows us how small atoms and molecules are. That means if you were to have like maybe a glass of water, then you probably have more molecules of water in that glass of water than there are stars in the known universe. So when we're counting large things in chemistry, we have a special value called a mole. And this value of a mole is kind of like the dozens or couples or googles that we talked about earlier. 1 mole is equal to 6.022 times 10 to the 23 things, or this is also known as 602 sextillion. So a really, 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 really big number. This is also called Avogadro's number, named after the guy who kind of originally posed this idea. So instead of saying that there are 4.7 times 10 to the 20 molecules in a drop of water, we can divide that number by Avogadro's number to make it in moles instead. And if we did so, we'd get a value of 0.0008, or 8 10,000ths. This is a lot easier to work with than this. Also, if we wanted to calculate the number of stars in the universe, we could say that there are 1.66 moles of stars. While we use moles in chemistry, they're kind of an idea that can be applied to anything. So you could have a mole of grains of sand. You could have a mole of cells in your body, for example. So where this comes from is it's based off of carbon. So Avogadro's number was first determined as the number of atoms in 12 grams of carbon, 12 being an important number to carbon because it's also the atomic mass of carbon, the sum of the protons and the neutrons. We also can use the atomic mass as a different value. It also tells us how many grams there are in 1 mole of a substance, since the atomic mass is recorded as being 1 mole of carbon. So we can use this to our benefit when we're trying to compare elements and how much mass they have per how many particles we have. For example, if we were to look at hydrogen and iron on the periodic table, hydrogen has a mass of 1.0078, and then iron has a mass of 55.845. And this is how many grams there are per 1 mole of this substance. So if somebody asked you, what is more stuff, 1 mole of hydrogen or 1 mole of iron? you should tell them, well, neither. 1 mole is going to be the same amount of stuff no matter what you're looking at, because a mole is counting how many particles there are. However, we know that 1 mole of iron weighs about 56 times more than 1 mole of hydrogen. So we could say that the 1 mole of iron is more massive than the 1 mole of hydrogen. And that's just due to the fact that iron is a much bigger atom. It has a lot more protons, a lot more neutrons, and it's going to be heavier as a result. So how many grams are in 1 mole of H2O, in 1 mole of water? We already talked about the water drops being a lot of things per drop, a lot of individual molecules per drops. And if we can figure out what the connection is between number of molecules and grams, we'll be able to know how much stuff there is in any amount of water. So let's think about it. If we look at the periodic table, hydrogen, like we saw before, is about 1.008 grams per mole. And if we look at oxygen, it's about 16 grams per mole. And a water molecule is 2 hydrogens and 1 oxygen. So if I want to know how many grams are in 1 mole of this, I could actually just sum up all of the different atoms that are involved, because 1 mole of water molecules is going to be equal to 1 mole of oxygen atoms and then 2 moles of hydrogen atoms, because for every 1 water molecule, I have 2 hydrogen atoms. So 1 mole of water molecules is going to contain 2 moles of hydrogen atoms. So if I add it all up, the 1 mole of oxygen is 16 grams. 1 mole of hydrogen is 1.008. I kind of rounded it to 1 here. So that means that the 2 moles of hydrogen is going to be 2 grams. So if I add up the 16 plus the 2, I end up with 18 grams. Now, this is called the molar mass of water. And it's called that because it is the mass of 1 mole. And we usually present it this way, of 18 grams per mole, so grams over mole. Because that tells us that for every 1 mole, we have 18 grams. For every 18 grams, we have 1 mole. This gives us a conversion factor to convert back and forth between grams and moles. And this is really useful in chemistry, because if you were to weigh out an amount of water, you could actually figure out how many moles of water molecules there were. And say you wanted to react that water with something else, you could convert grams of that to moles. And then when you compared the moles of the two things, you could actually directly compare how much of each substance you have. Whereas if you say were to compare 1 gram of hydrogen to 1 gram of iron, like we referenced earlier, it would be hard to know how many particles you had of each and what the ratio was between them unless you converted them to moles. So the molar mass of any molecule is basically the sum of the molar masses, or the atomic masses, of the particles that are involved. So an easy way to calculate the molar mass of any molecule or compound is by making an atom inventory and then adding up the mass of each atom. And what I mean by an atom inventory is looking at the compound or molecule, seeing what atoms are involved, and then taking the atomic mass of each and then multiplying it by however many there are in that substance. For example, what is the molar mass of iron 2 sulfate? We know this is called iron 2 sulfate if we look at our ionic compound rules. Sulfate is an SO4 2- polyatomic ion. And we know that this is a 1-to-1 ratio of Fe to SO4, that the Fe is also going to be 2+ charged. But that's besides the point. If I'm going to calculate a molar mass of iron 2 sulfate, I know that I have 1 atom of iron, 1 atom of sulfur, and then 4 atoms of oxygen. So what I need to do is take my atomic mass of iron, multiply it by 1, my atomic mass of sulfur, multiply it by 1, and my atomic mass of oxygen, and multiply it by 4, and then sum up all of these values. And then eventually I'll end up with the value of 151.91 grams per mole. So I know that if I have 151.91 grams of iron 2 sulfate, that I have 1 mole of that substance. And then I can also figure out, based off of any amount of grams of this substance, how many moles I have by using the molar mass as a conversion factor. Let's do another practice. What is the molar mass of chromium 3 nitrate? This one is a little bit trickier because we have parentheses, because we have multiple of a polyatomic ion. But if we just distribute the number outside of the parentheses like we would in math, we can figure out how many individual atoms we have. So based off of this, we have one chromium, which has a mass of 52. So we have 52 grams per mole from the chromium. The nitrogen, each nitrate has one nitrogen, but we have three total nitrates. So we're going to have three nitrogen atoms, which has an atomic mass of 14.01. So that'll give us the mass of all of the nitrogen together. And then we know that we have three oxygens per nitrate and then three total nitrates. That means we have 9 oxygens in the substance. So we take the atomic mass of oxygen, which is 16, multiply it by 9, and then we get 144 grams per mole. And now we can add these three values together and get a total molar mass for the whole compound, which will be 238.03 grams per mole. All right, so I kind of hinted at this, but we can use the atomic mass as a conversion factor. And we could do this using dimensional analysis, the skill we kind of worked on earlier in the year. And this is going to be really useful for basically the rest of the class because this molar mass stuff is going to be one of our most useful mathematical tools when we're talking about amounts of substances in chemistry. And just as a quick review of how dimensional analysis works, like say we had 24 inches and we wanted to know how many feet that was. That might be sort of an obvious thing to do in your head since these are units that you're familiar with, but let's look at the formatting of how we can use this math. So we have 24 inches. We want to know how many feet that is. So we're going to need a conversion factor. We're going to need a ratio that tells us what the relationship between feet and inches are. And we know that 1 foot is equal to 12 inches. So if we take our 24 inches and multiply it by a conversion factor of 1 foot over 12 inches, we can see that inches cancel out. We get units of feet, and then we do 24 times 1 divided by 12. And then 24 times 1 divided by 12 is going to be equal to 2. So we get a final value of 2 feet. So remember that when you have conversion factors, it's always going to be a ratio with two different units and a number relationship between those two units. And this conversion factor can either be oriented one way, like in this case, it's feet over inches. But if we wanted to do the opposite, say we wanted to calculate how many inches were in 2 feet, then we would take this ratio and we'd flip it upside down. We always want the unit that we're trying to achieve on the top and the unit that we have that we're trying to get rid of on the bottom of the ratio. All right, so converting between mass and moles in chemistry works the exact same way. So we can use the relationship of our conversion factor we can use our molar mass as a conversion factor as a relationship between the two units of mass and moles. So for example, how many moles are contained within 216 grams of pure carbon? Well, if we look at the periodic table, we can see that carbon has a mass of 12.01 grams per mole, which we can use as our conversion factor. So we're going to want to start with the 216 grams, the measured amount, and then we're going to multiply that by 1 mole over the molar mass, which is 12.01. And you'll see that grams cancel out. We'll get units of moles, and the value we get is 17.99. This is an old picture that I took, and I'm realizing the significant figures on this are wrong. If you actually wanted to report this to the correct number of sig figs, you'd have to round it down to 3, because that's what we have in our measurement. So the 9 would round up this 9, and that 9 would round up this 7. So this would technically be 18, but if we wanted to represent it as 3 sig figs, it would be 18.0. All right, next, this conversion factor, we can do the same sort of thing starting with moles and going 2 grams. So say we wanted to know how many grams were in 4.5 moles of pure carbon. Well, we could set up a similar mathematical relationship, but this time we're going to flip the ratio upside down. So instead of having moles on top and grams on bottom, we're going to have grams on top and moles on bottom. So if we have 4.50 moles, we're going to multiply that by 12.01 grams per mole. Moles cancel out. We get units of grams, and then we get 54.05 grams. And similar situation here, the sig figs are incorrect on this picture. We have 3 sig figs in our measurement, which means we should have 3 sig figs in our answer. So it'll be 54.1 grams. All right, lastly, or is this the last one? Okay, we have a couple more examples actually. So how many moles are contained within 65.2 grams of iron 2 chloride? Well, I'd want to figure out the molar mass of iron 2 chloride. So I'd take the mass of iron and then I take the mass of chlorine and I multiply it by 2, and then I'd add it all together. So we end up with this. So we have 65.2 grams. And then since we're going from grams to moles, I want grams on the bottom and moles on top. The grams cancel out, and I get units of moles at the end, and it's 0.51 moles. That should have one more sig fig on it. Sorry, the sig figs are incorrect in these examples. Let's do another one. What is the mass of 0.0048 moles of C6H12O6? So we have a bit more complicated of a molecule here. So we're going to want to make an atom inventory. So we have carbon, which has a mass of 12.01. We're going to multiply that by 6. We have hydrogen, which is either 1.008 or 1.01, depending on which periodic table you're looking at. We're going to multiply that by 12. And then we have oxygen, which is 16, which we're going to multiply by 6. And then we're going to sum all of that together. And we're going to get a total molar mass of 180.16 grams per every 1 mole. So in this case, since we're going from moles to grams, I'm going to want grams on the top of my ratio and moles on the bottom of my ratio. And one quick point, I've seen students make this mistake before where sometimes they'll always put the bigger number on the bottom. Remember that the value, that the mass that you calculate is always associated with the gram, and then the mole is always 1. A molar mass is always how much mass you have per 1 mole, how many grams you have per 1 mole. So we put the moles on the bottom so that moles cancel out here, and then we multiply that by that, and we get a final answer of 0.86 grams. All right, next, we have an experiment that requires 0.25 moles of magnesium and 0.5 moles of hydrochloric acid. So we need these in a 2-to-1 ratio. We need twice as much HCl as we need 0.25. And we want to know how much of each we need to measure out. So this is a good example of how this works in chemistry. I know that I need to react these in a 1-to-2 ratio, but their molar masses are going to be different. So I can't just weigh them out in a 1-to-2 ratio because the amount in grams is not going to be a 1-to-2 ratio. So first off, I'm going to need to convert those both to grams by calculating the molar mass of each. So magnesium is just a single atom, so we can just use the atomic mass from the periodic table, which is 24.3, and we can multiply that by 0.25 moles, and we end up with about we'll call that 6.1 grams of magnesium since we were only using 2 sig figs there. And then here we have 0.5 times 36.46, and we calculated this based off of the atomic mass of chlorine, which is 35.45, and then the atomic mass of hydrogen, which is about 1.01, and we summed those together. And both of these are going from moles to grams, so we have the grams on the top of the ratio and moles on the bottom of the ratio. And this tells us that at the end, we're going to need to weigh out about 6.1 grams of magnesium and about 18.2 / about 18 grams of HCl. And you can see that even though the moles were in a 1-to-2 ratio, the masses that we measured out are not in a 1-to-2 ratio, and that's because their molar masses are quite different. All right, in the previous problem, we had magnesium and HCl combined in a 1-to-2 ratio. Actually, I'm going to go over this in a later thing, so I'm going to stop the video here.